All right, we're on to section 11.6. We're going to talk about something called infinite geometric series. We want to be able to find the sum of an infinite geometric series if one exists, and then we want to also be able to use this to write repeating decimals as fractions. So we need a few definitions, so let's start there. In infinite geometric series, remember they go on forever and was adding up, and up, and up, and up, adding all the terms in a sequence that doesn't basically stop. So an infinite geometric series, by definition, is a geometric series with infinitely many terms. So if we don't say just find the first 6 or first 50, we want you to find the sum of an infinite sequence. Partial sum, this would be of an infinite series, can do one of two things. Is the sum, first of all, of the given number of terms in that sequence, and not the sum of the entire series. Okay? Only the sum of a certain portion of terms. When the partial sum approaches a fixed number, so it's starting to get closer to 100, as n increases, the infinite series is said to converge towards that certain number. Versus when the sums do not approach a fixed number, as n increases, the series is said to diverge. And if it diverges, which means it's not really getting close to a fixed number, there's no way you're going to be able to figure that out. And so that's going to be a nice and easy problem for you. You're not going to have to add up the terms of a divergent sequence. So knowing that, let's start with our first combination. So the sum of an infinite geometric series. The series has a common ratio r, and that r value has to be less than 1. So we're still talking geometric, so we do have that rate. Then the sum is going to be equal to that t sub 1 divided by 1 minus r, that rate. Now check the text because there was a nice little algebraic proof using subtraction of the sequences to arrive at this formula, so you can see where it's actually derived from. So if a geometric sequence has that common ratio and that ratio is greater than 1, then the related infinite series diverges and therefore does not have a sum. So the key is that you have that common ratio r, which we should be able to find in all our geometric sequence, and that the absolute value of r is greater than 1. If that's the case, then this diverges, and we're not going to be able to find out that sum, that one number, or supposedly that it's converging on. It doesn't have a sum. It keeps going forever and ever and ever. You will not be able to find it. But an infinite series can be used to convert a repeating decimal to a fraction. So we're going to show how to do that as one of our examples. So I think we're ready to go. We've now given a definition of when it diverges, etc. So here we go. Find the sum of the series 8, 9.6, 11.2, 13.824, and you can see and so on and so on and so on, if one exists. So it's your job to determine some of the key pieces. And the key players in that formula, again, remember we said the sum is going to be equal to S and T sub 1. So we've got our first term in our sequence, and 1 minus r. I don't believe we have our r value right now, so that's something we definitely want to calculate. So if you look at this right now, and we know it's supposed to be geometric, and you're saying, okay, what am I doing? Well, I can if I'm saying it's arithmetic, then I'm adding a 1.6 to get from 8 to 9.6. But then if I added that 1.6 in the next sequence or the next term, we definitely would have a mistake because a 9.6 added to a 1.6 does not give us an 11.52. So we have a slight mistake there. So we know at that point it's not arithmetic and it is geometric. So if it's geometric, you have that first term. 8 times some number is going to give me a 9.6, so do the math. 8 times some number gives me that 9.6. We divide by 8, and I think this is the one that we get a 1.2. Okay? So if it's a n value of 1.2, which really means that's our constant rate, or r, we ended up with exactly what they're saying here. R is our change agent, and the absolute value of r is greater than 1, so we have, by definition, the series diverges. It does not go to a single number. It does not eventually add up to be that single number. So it diverges, and we're done. Okay, easy enough. But you definitely do need to generate and find out what that constant rate is before you can make that divergent statement. So let's try a second one. This one's written in summation form. It says, find the sum of this infinite series. Now you can see right now it's infinite because right here in your summation, you have k equals 1 to infinity. Oh, so we have a slight problem. Right now we don't have anything like terms or, so let's generate a few, and that's always a good choice. So let's put a 1 in. If we put a 1 in, we get 1 over 1 plus 1 is 2, so 5 squared. You can multiply that out if you like. We'll go on. Put a 2 in. 1 over 5 cubed. Put a 3 in. 1 over 5 to the 4th, etc. So we can definitely see there's a pattern here. All right, now we should know our first term and we should know our second term. We should know our constant rate. So let's see the work here. If t sub 1 is 125 and t sub 1 or t sub 2 is 1 over 125, if you do that quick multiplication, taking the first term times some unknown r, it has to equal that second term. So first term times that rate has to give us the second term. That's all that really is. Okay? And so you do that math, and some of you can look at it written this way and see that it's a r value of 1/5. If that's the case, then you should now be able to put it into our formula, which was t sub 1, that's the 1 over 25, divided by 1 minus r, that r is that 1/5. So we get 1/25 divided by 4/5. You can use your calculator or you could use your fraction, yes, fraction multiplication instead of dividing. And you can do some canceling. You can see how you can cancel here and end up with 1/20. So the sum that this sequence would go to would be the number 1/20. Let's try another. Here is that example of what's going to happen when we have a repeating fraction. We should be able to use this same idea, but let's think of it slightly differently. If you think of that 0.04 with the 4 repeating as first, it has to be a 0.04. Then it has to be a 0.004, and then a 0.0004, etc., etc. You now start seeing the pattern. So you could think of this as 4 100ths, 4 1,000ths, 4 10,000ths, 4 100,000ths, etc. With that, if you do think of it that way, you could then say, well, t sub 1 is 4 100ths. R, you can see, is that multiplier. It's nice and easy to see. And if you can't, then you could still do that 4 100ths times some number n has to equal that second term 4 1,000ths. Okay, and when you do that, I think it's pretty clear to see that our constant rate is 1/10. Now, because that r value is 1/10 and the absolute value of 1/10 is less than 1, we know we have a series that converges. It converges to a number. Now, what is the number of this sequence? Because these numbers are getting smaller and smaller and smaller. So when we add them all up, they're going to hopefully get to something. Now, the question is what? So in this case, if we finish the math And I went back to decimals, you'll notice, using the formula. My first term, 0.04, divided by 1 minus r. Our rate was 1/10. I even turned that to a decimal. Worked all in decimals this time, 0.04 divided by a 0.9. You should know going from here to here that all I did was move the decimal 2 places to the right. So if I moved it 2 to the right here, I move it 2 to the right here, I have to add that extra 0. We're looking at 4 over 90. 4 over 90 is a fraction you can reduce. So when we reduce, we end up with 2/45. So now if you would grab your calculator just as a double check and see 2 divided by 45 on your calculator should give you a 0.04 with that 4 repeating. So we've shown you a little trick. So now if you do not know what some repeating decimals turn into and you don't have a calculator to your availability, you could always use this idea of the sum of an infinite geometric series formula. Okay, that's all for this section. You'll have a variety of problems to try, but bring any questions you might have with you to class.